Okay, I'm Matt Bauhoff in Petroleum and Geosystems Engineering at the University of Texas at Austin. This is the third part in our Matlab review videos where we're going to be talking about plotting, specifically 2D and 3D plots in Matlab. Matlab does a lot of fantastic things with plotting. It makes some beautiful plots. Just like in all the videos, I'm only able to scratch the surface and show you some of the bare minimum things that you can do. But it is very powerful, and I will show you enough to kind of get started and then let you go from there. So 2D plots is the most basic one, and we can start out really simple. So let me go through and show you how to make some plots. So here's an example where we can go in and we can create a vector. Let me clear all this out. We can create a vector x is equal to linspace from 0 to 10, and we know what that does. Creates a vector. This one's got 100 elements. Yeah, I have a. One thing about linspace, the last one tells you how many elements. If I don't tell it how many, then it assumes it's going to be 100. So x has got 100 elements in it, and then let's say I want to make a plot of 4 times x, or 4 times x plus 5. So I say y is equal to 4 times x plus 5. So I just want to plot this straight line with slope 4 and intercept 5. I can use a plotting routine to do that. Now, an important thing to note is that Matlab doesn't plot functions. It plots points. And that's a key thing. It's not going to plot 4x plus 5. It's going to use the equation 4x plus 5 and get different x values to calculate y values and plot the vector x versus the vector y. So we can know x, and now we know y. Y is a vector. I can look at y if I want to. Y has got 100 elements in it. So I got x and y. If I want to plot x and y, there you go. It just makes a nice plot. Plot x and y. X is on the x-axis, y is on the y-axis, and that's 4x plus 5. Right? It looks like a line. It's not really a line. What it is a bunch of points that are connected together, but it plots 4x plus 5. So good enough, but there's so much more we could do, right? So we got a figure that look like that. Now if I come over here, what if I didn't want that straight line? What if I just wanted to look at the points, and let's say I wanted to give them a color, like green? Well, I could plot x, y, and then put green asterisk. So I can go over here, and I can put plot x, y, green asterisk. You notice I use the cursor up button a lot because I like to cheat. I don't like to type everything out. So if I've already used a command or I use something similar, I like to use the cursor up to reprint it. But now I'm going to plot x versus y, but then a green asterisk. And what I get is this figure. So now it's just a bunch of green asterisks together, and they're not connected by lines anymore. And so I get a little different plot. Okay, well, that's nice. Okay, it gives me what I wanted. But there's so much more I can do with plots, right? So, you get something like that, and, oh, well, I used linspace of 10 there, so what I can do is, so it would have been a little bit more. X is equal to linspace. Let me use 11 points instead of 100. And y is equal to that, and then I can do plot. And that's how I got the one on there. So I only use 11 points instead of 100. But point's still the same. You can do a lot of different things. So I showed where we use green asterisk points. But you can use all these different colors I've got in the table. Y stands for yellow, M for magenta, C for cyan, R for red, G for green. All make sense. B is blue. Okay, if you wanted black, you got to use K. So some of them make sense, some of them not as much sense. I got tons of different symbols. I can use a period for a point, an O for a circle, an X for an X mark, etc. The lines, I can have a solid line, I can have a dotted line, a dash dotted, or a dash line. A lot of different options, and I can put those in there. And I might want to do a lot more kind of stuff. So imagine you're picking up your textbook from one of your classes, and they got a fancy plots in there. Well, they got a lot of different things going on. We want to kind of make our plot look really professional, something we might be able to publish or give to our boss or something. So a little plot that I got like this, okay, I'd be embarrassed to give that plot to my boss, right? But maybe if I did a lot of other fancy things to it, like put in X and Y labels and legends and titles and stuff, then maybe I'd feel better about it. So let's start by doing 2 functions, right? And I'm going to just do this. So let's say we've got clear. I'm going to say x is equal to linspace what did I do? 0 to 3, is that right? 0 to 3, and I'm going to say y1 is equal to 10 times exponential minus 2 times x. So it's going to create a vector y1, which is going to be given by that equation. Oh, it's not a capital X, it's a lowercase x. Okay, y2 is going to kind of look like it. Oh, yeah, so y2, I think is exactly what it's supposed to be. So y2 is equal to 12 times exponential minus 3x. Okay, and let's say I want to plot both of them. I plot x1. I can plot x versus y1 and x versus y2. Now this is a very important point, so pay attention. When I want to plot two curves, I got to put my first x and my first y, my second x and my second y. I can't just put x, y1, y2. That wouldn't work. It would give me an error. I'll try it. Watch. It doesn't like that. Okay, I got to put x, y1. Okay, and it might have been an x1 and an x2, but in this case I use the same x. But x, y1, x, y2. Or x1, y1, x2, y2, whatever my variables are. But that's what I have to do. When I do that, I get a nice plot that looks like this. Oh. There you go. So I've got my 1, it started at 12, it started at 10, and they're both exponential decreasing functions. Still not great. What else can I do to this? So that's what I got. I got something like that. You can do different things. I don't use all of these, but you can prescribe the minimum and maximum x and y axes. You can draw grid lines, so you can use a grid on or grid off. You can put a legend. You can add text to your figure. You can do x and y labels. You can put a title. A lot of those things we want to do. So let's do, here's a neat thing. This is an exponential plot. What if we wanted to make our axes log or semi-log? Let's do that. So I could have done, so this is my plot. I think, is it a little log? Okay, that's a log-log plot where I got a log y-axis and a log x-axis. This is a semi-log x. So if I do that, it makes the y-axis linear and the x-axis log. Well, okay, I don't really like that one. Let's do semi-log y, where the y-axis is logarithmic, but the x-axis is linear. Oh. Well, that's a cool way to do it, right? Because then it makes it look linear. So the y-axis is logarithmic, the x-axis is linear. Because it was an exponential plot, both of these are linear. So that's a nice way to do that. Another little feature, I can use the grid command. If I do grid on, then it puts grid lines on there. And so that's kind of an interesting way to do that. Might make it a little bit more professional. What else I can do? So that's what I said there. So semi-log y makes the y-axis log, x is linear. Oh, I did something else there. I wanted to use a red line for the first one and a blue line for the second one. So let me do that. I got to do it after. I got to do x, y1, then I put red line. And then I can do a blue, which one did we use? We use a blue line again. Okay. I could have even done a blue dash line if I wanted. Cool. So I did that, and I put my grid on. What else? Okay. I can do, I can change my axes lengths. So if I don't tell it how far I want my axes to go, my x and y axes, then it just chooses the default, whatever it thinks the way you should do it. But in this case, maybe I want x to go from 0 to 2.5. Maybe I want y to go from 0.001 to 50. So I can go in there, and you got to make sure you do this right. It's axes, open parentheses, close open brackets, 0 to, what was it? 2.5. And then the y, I want to go from 0.01 to 50. Was that it? Or was it? Yep. Close brackets, close parentheses. And if I look at my figure now, then x goes from 0 to 2.5, y goes from 0.001, 10 to the minus 3, to 50. So it's exactly what I told it to do. All right, what else can we do with this? Let's see. We include a legend. Okay, so maybe this is something that happened on Monday, and the other plot is something that happened on Wednesday, and then I could put the I can either. Well, let me show you both. So let me go. So I can make a legend, and I can say the first figure is going to be for Monday. Is going to be something that happened on Monday. The second one is going to be something that happened on Wednesday. All right, and when I do that, cool. A nice legend comes up. Maybe I don't like the position of the legend. Okay, Matlab chose a position for me, but I want to put it somewhere else. I think if 1 is this, I think 2 is there, 3 is there, 4 is there. Let me see if that's right. So I'm going to redo it, but now I'm going to tell it the position is going to be 2. Yeah, just what I thought. It moved the legend to over there. So that's like the 1 position. That's a 2. That's a 3. That's a 4. Otherwise, it just chooses where it wants it on its own. That's kind of a preference. Oh, maybe I want a title. Okay, maybe this is temperature. This is temperature that happened on Monday, and this is temperature that happened on Wednesday. So I'm going to say title, temperature curve. Okay. Well, there you go. I got my title there. I don't like how small it is. That's a small font, so I'm going to change that. I'm going to tell it font size. And I forget. Do I got to put, yeah, that's what I thought. I got to put parentheses around font size. Great. Now it made that font bigger for the title, so I like that. Oh, what else can we do to my figure to make it better? Oh, I put labels. Okay, there's a figure is useless without labels. So maybe on the x-axis is time, and the y-axis is temperature in degrees C. And, I want to make sure I got a big font size on this too, so I'm going to tell it font size is 12. So I can do x label, okay, time in seconds, okay. And I could end it there, or if I want to put my font size, then I can do font size. See if that worked. Cool. I got a label, time in seconds. Let me do the y label too. Do my little trick with the cursor up. I'm going to do temperature. I misspelled that. C. Font size 12 also. Check my figure there. Cool. Now I got that. That's good. Anything else I want to do? Okay, so what about my axes? I want to make my axes like 0, 0.5, 1, 1.52, and then this 10 to my. I want to make the font a little bit bigger. That's kind of tricky, but you can. There's some things you can do if you go to File, you go to Edit, your figure properties. There's a lot of things you can do in here that'll allow you to do it. You can change your font and stuff like that. That's one way to change a lot of your things, but it's easier to do it at the command window if you know what you're doing. So I'm going to go over here. And unfortunately, there's no easy way to do it like the font size before. Instead, what you have to do is you have to say set. And this is something I don't use enough, to be honest. This is set GCA. That means get current access. That's what GCA stands for, get current access. And we said we want to make, in that current access, we want to make the font size. I'm going to make it really big just to show you how obvious it is that it changed. So you believe me, 16. Oh, see how big the axes changed? All right. One other thing I don't like in MATLAB plots, I don't like the gray background. So I'm going to set, not GCA anymore, just hit GCF, get current figure, and I'm going to make the color, I think is it going to be, let me see if that's right. I'm going to make the background white. Yeah, exactly what I thought. So we're going to set, we're going to get the current figure, the one we're looking at, and then we're going to make the color, we're going to make it white. So let's do that. There we go. Now that's a pretty good looking figure right there. All right. I probably made my axes too big a font, so maybe I'd go back and do maybe make it more like 12, right? Yeah. But otherwise, I think that looks like something that you'd see in a textbook. All right, that's one of the things I love about MATLAB is the cool figures that it makes. Way better than anything Excel will ever make. I tell my students that work for me in the research lab that they're never allowed to make a plot in Excel. It's all got to be in MATLAB because they're so much more professional looking. So I'm going to show you one more thing to do. That's our figure. Let's say we wanted to print it as a JPEG. So I'm going to say print it. The command you use is -d JPEG. That says make it a JPEG. Tell what resolution you want it to be, like R300. That means a 300 pixel resolution, and then whatever you want to name it. So I'm going to call it my temperature dot JPEG. Oh, I should have put apostrophes around it. So this is going to print in JPEG format, 300 resolution, create a file called temperature.jpg. Do that. I'm going to type ls to make sure it's in there. Temperature. There it is. So let's go look at it. Let's go over here. And there it is. So I got a little JPEG there. So now I can do whatever I want with it. So that's a good looking plot, all right? There could have been some other things we did, but I think this is in pretty good shape. All right? Not a whole lot more I'd want to do with that kind of figure. Okay. That's most of what I want to talk about with 2D plots. There's one or two other things I wanted to show. Another one is subplots. And with subplots, what you can do is you can put a bunch of plots together. So I can have like almost a matrix of plots, so it looks like. So what you can have is like 3 rows and 2 columns. You can have a bunch of small plots and right next to each other. And what you do is you use the term, it says in plot, you use subplot. And so let's say you want to have 12 total plots, and you wanted 4 columns and 3 rows of them. So you put 4, column 3, and then you make each plot one at a time. So you might have like 12 plots. You just tell which plot you want to do. If it's a 7th plot, you would write 4, 3, 7, and then you would go and proceed to do it. So I'm not going to type all this in MATLAB. I'm going to let you do it. So maybe pause the tape right now and just type in what we get right there. Okay, and just try to get it to work. Type it word for word and make sure your 4 plots come up. So pause it, type in those, 9 commands, and we'll move on. Okay, so back to the video. You should have gotten plots that look something like this. So you made a 2x2 matrix, if you will, of subplots where you had sine of x, sine of 2x, sine of 3x, and sine of 4x, and you should have gotten something that looked like that. So that's kind of a neat way to do plots when you have multiple and they're kind of related. So, so you should have gotten something like that. And, well, let's see. I'm going to show you one other thing with 2D plots, something I don't use very often. Well, let me show you, I'm going to show you one other thing. So I'm going to go back. let's do our, what did we have? We made our x and our y. I'm going to do a y, I'm going to create a y3. y3 is equal to 10, right? And remember I had my, oh, I'll show you a couple things, I guess. Remember we did this. We created a plot that looked like that, right? Remember, that's how we started. What if I wanted to use different axes for the, let's say I was plotting gas rate on one, and I was plotting on oil rate on the other. They don't really have the same axes, right? I mean, your oil rate is going to be in barrels per day. Your gas rate is going to be standard cubic feet per day. They're not going to be on the same scale, but you might want to put them on the same plot. You can use something called plot YY. I don't use it a lot, but if you do X and Y1 and X and Y2, what it does is it creates something, and you see the blue curve goes from 0 to 10, and the green curve goes from 0 to 20, and so it's got on different scales. Right? Now, this is not necessarily an example where you do that, but the example I gave with oil rate and gas rate would be a case because they're used different units, they're different scales. So you can put them on the same plot, and it just makes the scales different. So this plot would correspond to that, and this would correspond to that, and that's how you use the plot YY. Let me go back to the original plot I had, which was just the regular plot, and we had that. What happens if I decide afterwards, well, I really wanted to add another plot to that? I can use a hold on command, and then I could say plot x, y3. Okay, then it adds it to the current plot. If I hadn't used the hold on, it would have deleted it. So let me do that again. So I do that. Oh, I think it would have. I do that, and it does that. And then I do and then it deleted it and does another one. So if you use the hold on, then it holds on to the current plot. Any new plot you make, paste it on top of there. So that might be something you want to do. One more thing with 2D plots. I don't use this at all, and I should. It's called FPlot. And FPlot allows you to plot a function, just type in the function. So it's sort of a weird way of doing it. Use the @x command. And then let's say I wanted to plot sine of 1 over x. So I do sine 1 dot backslash. Okay. And I use that dot because I want to do element by element. Okay. I can't divide 1 divided by a vector, but I can divide 1 by each element of the vector. That's why it's element by element division. Okay. And let's say I want to do it from 0 to pi. 0 to pi. Okay, let's think about what this says. I want to plot the function sine of 1 over x. I want to go from 0 to pi, and the @x just means that that's the variable that I want to change, x. Okay, I thought that was going to work. Oh, I needed to put parentheses around the x. Okay, and this is my plot of sine of 1 over x. Let me show you why I had to put that a over x. Let's say if I defined a is equal to 2. Okay, and maybe I was doing sine of a divided by x. Okay, if I wanted to plot, then Matlab really wouldn't know whether or not a was my dependent variable or x was my dependent variable. So by saying a of x, it knows that x is what I want to change. X is what I want to vary from 0 to pi instead of a. So if I do that, I get that, okay. But if I had done out of a, I bet that'd probably give me a really weird looking plot. We'll see what happens. Okay, I get something really strange. But the point was that in the first case, I was varying x by keeping a at equal to 2. In the second case, I was varying a, and I don't know what x would have been. Probably something I defined earlier. But yeah. So that's how you use FPlot. You can plot just a function and just define the function. I don't use FPlot very much. I know people who do, and they claim it's really powerful. So maybe I should be using it more. Let me clear all this. Clear all. let's talk about 3D plots. You're going to use 3D plots quite a bit, especially if you're watching this for my reservoir simulation class. 3D plots let you plot a variable as a function of two other variables. So instead of just y as a function of x, you might have pressure as a function of x and y, or x and z or something. And that's really common. And in reservoir simulation, we're going to be doing stuff like that all the time. So you'll really need to understand how to make XY plots. So let me try to explain how we do these kinds of things. So these are 3D plots. And there's, I think, dozens at least of different commands to create 3D plots. I'll just cover a couple, the ones that I think are useful. You can use the mesh command, and it kind of creates a 3D plot that looks like a mesh. You can use the surf command, which creates a surface plot. There's also a contour plot you can make. Basically, the idea is that you're plotting z as a function of x and y, for example, okay, or z it could be temperature, whatever. But the point is that that's a function, in two different variables like x and y. And just like in 2D, we don't plot the function ever, we plot points. And so either you're given points and you plot them, or you have a function and then you use the function to create points and you plot those points. So the idea is that at different values of x and different values of y, you evaluate your z and you plot that z point, and you just kind of build it together, and then you connect it and you make a surface or a mesh plot, something like that. And that's kind of what we're doing. That's the general idea. Let's talk about how we do that. The simplest case is that we just have matrices of data. So I give you a matrix of x's, I give you a matrix of y's, and I give you a matrix of z's, and then we plot them. All right? So I don't know. I'm going to try to show you how to do that. I don't know if this is going to work well or not, but let's just say x is equal to a bunch of random numbers from, and let's say it's going to be 50 by 50. Or I'll do 20 by 20. Or 20 by 30. I can even do that. Let's do that. So it's going to be random numbers between 0 and 1. Y will be a different set of random numbers between 20 and 30. I should have put my z is another set of random numbers. Okay. And now I'm going to do a surface plot. And this will probably, because these are random numbers, it's not going to be a pretty plot. I don't know what it's going to look like, but let's just do it. Okay, so it makes this weird looking plot right there. They're all random numbers. But the point is that I had a matrix X, I had a matrix Y, and a matrix Z, and they're all the same size. And Z, the element Z corresponded to the element X and the element Y. So I picked my X and Y and I plotted the Z. So the idea is it looked like this. So we had my X, Y, and Z matrices. This value of X, this value of Y, okay, think of that as being a Cartesian grid, like a grid on the bottom. You find your x, you find your y, and then you plot your z value. That's how it is. So this x and this y correspond to that z. This x and this y correspond to that z. This x and that y correspond to the next z. And that's all you have to do. And your syntax is really simple. You just say surf xyz or mesh xyz, and that's all it is. No big deal. That's if you've got the matrix. If you've got this x data, you got this y data, and you got the z data, then you could just do that. And then you could do other things, okay? You can make some, add legends and axes labels and all the stuff we did in 2D you can do in 3D too, okay? But these are some different ways to do 3D plots. Now, a lot of times what we have is we don't have the actual matrices, we've got an equation, okay? If you've got an equation, then you've got to use the equation to create your matrices and then do that. And sometimes that's not so simple. Right? So let's say we know, and that kind of comes in steps. So all I know is I give you a function that z is equal to, let me see if we'll get there in a second, but we're going to use something called mesh grid, which isn't a plotting tool at all. Mesh grid is just a way to create a grid on a Cartesian grid, kind of like the picture I've shown right there. And let's say I got an x and a y vector. So let's say, and we'll get there in a second, that x goes from x1, x2 to xm. So maybe it goes from 0 to 10. So I got 0, 1, 2, 3, 4, all the way to 10. And y goes from 0 to 20. So 0, 1, 2, 3, 4, all the way to 20. That's what x and y looks like. And my goal is to make this mesh. Right? So that's it all over here. So for every x is equal to 1, there's 20 different y's. So when x is equal to 1, y is equal to 0, 1, 2, 3, all the way to 20. When x is equal to 2, y can be equal to 0, 1, 2, 3, all the way to 20. So it's kind of on this grid where we do that. And we can use the mesh grid command to create that. The way the mesh grid command works is like this. Is that if I've got a vector x and y, I'm going to basically use those vectors to create matrices which have the same information. So you start out with this. I've got a vector. So my matrices x and y start out like this. And what they're doing is they're just pasting the rows on top of each other. So at my value of x1, I've got all these different y's. y1, y2, y3, all the way to yn. So x1, 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 x1. And then you got y1, y2, y all the way to the end. That's what I show right here. So this is y1, y2, y3, y, and they always correspond to the same x1. That's why x never changes and y is. Then I move on to the next one, and x is equal to x2 now. That's why I got x2's all the way down here. But then y goes from y1 to yn again, and then you continue on to the whole thing. And now I create my matrices x and y. In each of these points, x1 and y1 correspond to a different grid, a different point on my grid, right? So if I had n in this direction, m in that direction, that's n times m. That's the total number of points. And I've got matrices that are n by m matrices. All right, so that's good. So now maybe we can just do an example. Let me... I'll come back to it, I guess. So let me show you an example with that. So let's say, I'm going to keep it simple. I'm going to say x is a vector which goes from 0 to 5. Goes up by 1s. And y is a vector which goes to 8, by 2s maybe. Okay, so those are both vectors. If I say mesh grid, x comma y, it kind of maps those little vectors x and y into matrices capital X and capital Y. And so you get a matrix x and a matrix y, which look like this. And if you look at it, x just repeats itself down these columns, but then, or the x vector is repeating itself over and over again on the rows. And then y, the y vector is 0, 2, 4, 6, 8 is repeating itself over and over again. But each element, 0, 0 is unique, from 0, 2 is unique from 1, 0, etc. So we've got, let's see, that's 5, 1, 2, 3, 6. We've got 30 unique points, x and y, and they're basically just on a nice, regular Cartesian grid. Now, back to plotting. Mesh grid didn't do any plotting. Mesh grid was just a way to convert vectors into matrices on this grid. But we want to use it to create these things. So let's say we wanted to plot a function, and it's a really easy function. Z is equal to x squared plus y squared. All right? So let's do that. Let's create a new function, which is z, which is equal to x squared plus y squared. And I did something wrong. Don't press the enter button yet. What I wanted to do is use the element by element notation. Why am I using the period notation? Because I want to square each element of x and I want to square each element of y. I don't want to actually square the matrix. I don't want to do x times x. I want to do this x squared and this x squared, each one of these elements of x squared and each element of y squared, and I can create a new matrix which looks like this. So now, this value of x, for example, and this value of y correspond to this value of z, right? And then I can make my plot. So now I can go and I can do surf or mesh or whatever I want to do. So surf x, y, z. All right? Or I can do mesh x, y, z. Okay? And it's that simple. let's see, where's the figure? Okay, that's what a mesh plot looks like. And let's finish up by doing this little example I've got here. So let's just do an example that looks like this. So we got a vector that goes from minus 10 to 10 and increases by 0.5. And I mean, this is basically the same kind of picture we just showed a moment ago, but a little bit more complicated, a little bit more detail to it. Y goes from minus 20 to 20, create my mesh grid, then I create Z, which, see, you see the step with the mesh grid, X and Y, you just create matrices so that it can do the mesh grid. And then Z is equal to X squared plus Y squared, and then I can make my plot. So really the same thing. So what did we have? We had minus 10 to 10 and minus 20 to 20. So we can say, well, I'm going to clear everything. Right, and then Y, I think we went from minus 20 to 20. I'm going to create my mesh grid. So I'm going to use, I don't have to call it capital X and capital Y. I can call it whatever I want, but that's just what I chose here. Okay, and then I can do Z is equal to X squared plus Y. If you want to put in a more complicated function, go for it. Okay. Not sure how I got that function there. So I think maybe what I'm plotting here is a little bit more complicated function than what I had done, but same basic idea. And then, oh, you probably would never do this, so it's not all that useful. But that kind of finishes what I had here. Let's do example problems together. So we've been doing some things, and what I'd like to do is to do some example problems that you can follow along with. Let's go to the dot cam. Okay, now I'm going to go through these really quickly. I think that my plan is for you to pause the video when I show the problem, for you to work it out on your own, and then for you to go in and do it yourself in Matlab, and then come back to the video and I'll show you the results. So I'm going to just show the problem or describe it, and then you pause the video, and then I'm going to show the result. So let's say we got a matrix K. It's a 3 by 3 matrix, a vector grad P. So it's the gradient of P, and it's got an X, Y, and Z component, and a grad Z, which has got 3 components. A scalar, we'll call rho G, is equal to 60, and a viscosity mu is equal to 0.7. Now, I'd like to point out that doing subscripts and Greek variables and stuff is not easy to do in Matlab. So instead of using the mu for viscosity, just use V or VISC or something. So as an exercise, create each of the matrices, vectors, and scalars. So create K, del P, you can call it something other than the triangle thing there, the gradient, something the del Z, the rho GZ, and mu. So create those 5 things. Then determine the YY component of the permeability. So that's this. Then calculate the velocity vector using Darcy's law. So that's the velocity is equal to minus the permeability tensor divided by the viscosity, and grad P minus rho G del Z. That's Darcy's law. So I want you to do that very simple thing. It should just take you a few minutes. And pause the video, figure it out, and then when you're ready, turn the video back on and I'll show you the results. So we're back. Hopefully you did that problem yourself. Okay, so let's create K. K is equal to 108, space 2, space 5. That's the first row. Then it's 2, space 12, space 3, semicolon. Then it's 5, space 3, space 10. All right. That's K. That's my matrix K. I'm going to call my, you probably may have called it something different. I'm going to call it a grad P, and it's a column vector, so it's 50, semicolon, 200, semicolon, 100. Then grad Z is equal to 0.3, semicolon, 0.2, semicolon, 0.4. All right, and then row G, I just use row underscore G, is equal to 60. And viscosity is equal to 0.7. All right, so I got that. And then the first thing I asked you to do, well, that was the first thing I asked you to do. You created all the matrices, vectors, and scalars and all that. Then the next thing we could do is calculate the YY component. So that is, K was a 3 by 3 matrix. We wanted to get the value 12, which is the second row, second column. That's the YY. So I just do K through 2. It's 12. Or I could have called it KYY. It's equal to K through 2, right? If you wanted a whole row, let's say I wanted the second row, but all columns, that would give me that, right? But that's not what I was asked for, right? Usually we wanted the KYY component. That's the second row, second column. Then the last thing I asked is to do Darcy's law. Well, that's simple. You just put in the equation. U is equal to K. Well, actually, I'm going to go back to the screen here, and we'll make sure that this is going to work out. Can we really do this matrix vector multiplication? This is Darcy's law. So K was a 3 by 3 matrix, and I multiplied it by, well, grad P was a 3 row by 1, Z was a 3 by 1, rho G was a scalar. So 3 by 1 times a scalar is just a 3 by 1. I can do a 3 by 1 minus a 3 by 1. That was the del P minus rho G Z, so I get another 3 by 1. And then K divided by viscosity, that's K divided by a scalar, so you're just left with a 3 by 3. And then if you did a 3 by 3 times a matrix times a 3 by 1 vector, inner dimensions have to agree, and I'm left with a 3 by 1. So my velocity vector should be a 3 by 1. Does that make sense? Of course it does. Velocity can have an x, y, and z component. So it's a 3 by 1 vector. So let's do it. So U is equal to minus K divided by, what did I call it, viscosity, times grad P minus rho G times grad Z. And what happens? I get my U vector. So that's my velocity vector. Got an x, y, z component. It's a 3 by 1. So that works. So that's problem number 1. Let's move on to problem number 2. Problem number 2 looks like something you learned in Reservoir Engineering 2, maybe. So recall from Reservoir 2 that the pressure increases radially away from the well by the following equation. So you remember that ugly exponential integral equation. By the way, in Matlab, there is an exponential integral, EI, in there, and you could use it directly. And so you can actually call that function, and it would do it. We're not going to do that here, but if you wanted, you can look up Matlab and do it. I've done it before. But there's an approximation to that, which is this logarithmic. So it's pi is equal to q over mu, 2 pi k, h, ln of phi over, the porosity, viscosity, compressibility, r squared over 4kt, plus 0.577. So that should look similar to you. So what I would like you to do is to make a plot. So first, create a vector that goes from 100 r points logarithmically. This is kind of a log plot, so it's good to do a logarithmic length from 0.001 to 100. Maybe we have to use log space for that. Then we want to create a vector of pressures that correspond to the points r by the following equation. So we're going to use this equation and the r values to create p. So we'll have a vector r and a vector p. Then the next thing I'm going to do is to create a second vector, which is an approximation to that data, and I've got it saved in a file called pressure.dat. So if you've got access to that file, if I send it to you, then you can use it. If not, you can probably just skip parts 3 and 4. Then I ask you to calculate an error vector, p minus p apparent, and maybe calculate the error using an L2 norm. If you forget what an L2 norm is, I'll show it to you when I do the solution. And then 5, plot the analytical versus the numerical solution as a function of r, and use appropriate labels for titles and legend and all that kind of stuff. So, so there's the problem. Okay, pause it right now and do it yourself. When you're ready, turn the screen back on, and I'll show you the solution. So I'm going to start from scratch. I'm going to clear all. And we want to increase logarithmically. So I'm going to say R is the log space. And we wanted to go from 0.001, so that's 10 to the minus 3, so minus 3. We want to go to 100, so that's 2. And we want to increase by, we use 100 points. So that's going to be R. Now, I'm going to just use a semicolon, so I'm going to assume it's right. If you wanted to look at R, you could not use a semicolon. Then I want to make a vector of pressures. Well, that's pretty easy. It's P is equal to 100 minus 10 times we want to use the ln, but remember in Matlab it's not ln, it's actually log. So 10 times log of, and I made the equation really simple, r squared. I'm going to use the period notation because we want to square each element of r. So that's the element by element exponentiation. So it's r dot exponential 2. That means to do the second exponent to each element of r. So we got that. So it's the ln of r squared plus 0.577. So I should, and I can look at whose. So I've got r is a 1 by 100, 1 by 100 vector, and p is a 1 by 100 vector. So I've got r and p. That's good. Now, what did I want to do? I wanted to open up my pressure.dat file. Let's look at pressure.dat. Pressure.dat looks like this. It's a nice, easy file. Some of you may have used load. Some of you may have used import data. That's fine. I'm going to show you how to do it with the fscanf. It's a little bit uglier way to do it, but it works, and I just want to give you some practice. So what I'm going to do is I'm going to open that file. FID is equal to fopen. Pressure.dat. Okay. FID is equal to 7, so it read it in good because I got a positive integer. The next thing I want to do is, let's see, I didn't have any lines of code, so then I'm going to do d is equal to fscanf FID And these were real numbers, so I'm going to use the %F symbol, right? F stands for floating point number. So I'm going to scan in the file, pressure.dat is given by the file identifier, and I'm not going to use integers, I'm not going to use strings, I'm going to use real floating point numbers. That's a %F. And I'm going to do that, and I'm going to just do that so we can look. So you see it read it in as a vector, even though my data was kind of in a nice matrix form. Right, so now I got to reshape it. So I'm going to use my little reshape trick, and I'm going to say, well, what did I say? I'll call that D. Yeah. So maybe we'll call it A is equal to reshape. What do I want to reshape? I want to reshape the vector D, and I want to have 2 columns and a bunch of rows. But remember our little problem with fscanf and how we do the reshape. So I actually have to do 2 columns and 2 rows, and the number of columns would be the length of D divided by 2, and then we're going to have to transpose it. So I know, really weird way of doing that. Try to understand why we do that, and it'll make more sense. So then we do that. Oh, I did something wrong there. Oh, length of D, not length of 2. Okay, so this now looks like my data file, right? My A matrix is what I called it. Looks good. 234. Yeah, so that's right. Okay, so I got that working. And now, if I want to just know what my pressures are, that was the second column. So I could say P, I don't know, P app or something is equal to, don't call it P because I've already got a vector called P and I want to use it. That'll be all rows, but only the second column. Okay, so that's that. All rows, but the second column. Oh, not D, A. Okay, so I make a lot of mistakes. You see that I do that. That's okay. Everybody who does programming makes mistakes. Just don't get frustrated. You know, you're going to make a mistake. You try to figure out what you did wrong, and then you correct it. So now I got P app, and if I look at whose, I've got P is a 1 by 100, and P app is a, oh, actually I don't like that. What is P? P is, okay, I'm going to say P is equal to P, so they're the same size. So now I do whose, okay. I transpose P so that P and P app are the same size. Now what it asks me to do is create an error. Error being the difference between P and P app. So I'm going to say E is equal to P minus P app. That's the difference between the two. Alright, there you go again. Well, I called it that. Okay, so you can see that there are small numbers in the errors there. And I promise to explain what a norm is. A norm is a kind of scalar measure of error. You should have learned this in 310. But a norm, an L2 norm is a square root of all the elements of E squared. So it's so if I got E1, E2, E3, all the way to En. Okay, the norm would be E is the square root of E1 squared plus E2 squared plus E to the N squared. So it's always going to be a positive number. It's always going to be a scalar. It's a measure of error. So if your E's were, I shouldn't call this E. I should call this. This is my L2 norm. And sometimes it's given by that symbol. So I'll calculate my norm of E. Then what I could do is I could use a square root command. I don't think we've used a square root command yet, but it's the square root of E. I'm going to transpose times E. So that's a row times a column vector. That's a scalar. It's a dot product, so then I take the square root of it, and I get 69.1473. That's my norm. Okay. Now the last thing I wanted to do is make a plot. So that's kind of going back to what we had over there, and I wanted to make a plot of my radius versus pressure, and also my radius versus my pressure measured from the field. So let's do. I'm going to do it on a log-log plot. Okay, because it's kind of a logarithmic plot, so I think maybe it worked better that way. I'm going to do R versus P, and then I'm going to use black line for that. That's good. So I got that. And then I'm going to do R versus P apparent, and I'm going to use a blue circles for those. Okay, as a general rule, okay, as engineers and scientists, we always plot equations or models as curves. We always plot data as points. So that's why I've used the black line for the model, the equation, and the blue points, the circles, for the data from my file. And so if I do that, I get something that looks like this, right? Looks pretty good. My black curve is the blue, and then my blue dots are given in there. And so this is a log-log plot. I could have done a semi-log or just a regular plot or something, right? But that's just not what I did. I can do grid on if I wanted. Oh, what happened there? I don't know why I got rid of the... What do we do? There we go. So my grid's there. What else do I want to do? X label. Radius. Okay. Put my units. Feet. Y label. Pressure. PSI. Okay. Legends. Analytical. And then the other one will be, let's say, measurement. Or whatever. Okay, there's my legend. Okay, I could change font size and stuff like that if I wanted, and do some of those other things I talked about earlier. Now, if I wanted to, I could print. I don't want to call it that. I'm going to call it well test or something. All right. Okay, and if I go in my file, should be in there. Okay, there's my well test plot. Right. So I can. Now I got my pressure versus radius. I got my model. I got my data. Pretty cool plot there. All right. So let's finish with one last example. This is something else you should have learned from Reservoir 2. We're going to make a 3D plot now, I think. Make a contour plot. See here, we're doing time. Okay, so the last thing we want to do is recall from Reservoir 2 that a pressure in a 2D homogeneous reservoir can be approximated by an analytical solution of Ploss's equation and a theory of superposition. So what you had is you had this summation here. This is mu divided by 4 pi kh. These are rates. And then your xi, yi are your positions of your wells. And that's what your pressure field looked like in there. One particular reservoir has a producer at 0, 0, and injectors at minus 100, minus 100, minus 100, 100, 100, minus 100, and 100, 100. The equation can then be written, if you just expand that out and put it in there, it looks like this. So this is our equation, P of x of y. And what I asked you to do is create a surface plot. That's the surf command. That's surf. Remember we learned surf and mesh. There's also a contour, okay, and I didn't teach you that, but it works exactly the same way. Instead of saying surf XYZ or mesh XYZ, you do contour XYZ. So you can make a contour plot that way, and I asked you to make a contour plot of those things. So, again, here's the problem. I don't know if you can see it well enough, and there it is. Pause the recording, do this problem yourself, type it into Matlab, come up with some nice 3D plots, surface and contour, and then start the video up again, and I'll show you how we can do that in Matlab. Okay, we're back, and I'm going to show you how to do this in Matlab. We wanted to make this plot, P of X and Y, and what do we want to do? So we know that the injectors are kind of, well, the producer's at the center, okay, and we kind of think of it as a square, and we've got, maybe I'll draw a picture. Let me go back over here. Okay, so this is minus 100, this is 100, 0, 0, 100, 100, 100. We got a producer right over here, right? We got injectors at the edges. We want to make that plot. So our X goes from negative 100 to 100. Our Y goes from negative 100 to 100. Nope, that picture not come out well. Okay, so we got negative 100 to 100, negative 100 to 100. We got a producer at the center, injectors along the edges. Now let's make a nice fancy 3D plot to do all that. Increase by ones. Okay, that's X. I'm going to make a Y vector, which also goes from minus 100 to 100. All right, those are two vectors. You could have used linspace, by the way, instead of my colon notation, but I like the colon notation better. Now we want to use mesh grid to map those vectors onto grids, to kind of create our Cartesian grid where we can use our equation to evaluate our points. So now I'm going to do X comma Y, and that's going to be equal to mesh grid X. Okay, and I like to use a semicolon so that I don't have to see the because these are huge matrices, right? They're each going to be 200 by 200 matrices. I don't want to look at them, so I'm just going to put the semicolon there, and then well, I misspelled it, but okay. And if I want to see what's in there. I got a capital X, a capital Y, a lowercase x, and a lowercase y, and those are the sizes of those. So that's kind of what I expected. Now I'm going to use my equation to evaluate the value. Now some of you may call it Z. I'm going to use the variable P for pressure. And I'm going to use, remember we're doing, these are logarithms, ln, but in Matlab that's log. And it's going to be minus a log, open parentheses, the second open parentheses, capital X minus 100, close parentheses, element by element notation, so it's the period, caret, 2, right, plus y minus 100, close parentheses. Let me see if I did that right. Yeah, so that's my first term. And so that's like one of my injectors. Now what I'm going to do is I got to write the other 3, but I'm lazy, so I'm going to copy and paste and then make changes where necessary. So I'm going to do the plus. I'm going to do the what's there. If I didn't mess something up, then I can do. I think that this will work, but you can do something that's this little. Oh no, that didn't work. Never mind. Let me go back over here. And then we had 100 at the end, right? So we had 100. So you should have had something like that. Hopefully I did that right. Oh, maybe not. What does that not like? First of all, it's supposed to be a negative. Okay, that worked now. Okay, so hopefully you put in that equation right. If you need to, pause the video and look to see what I wrote. This is how I did it. I think I wrote that incorrectly, but we'll find out in a moment. Let me now plot it up. Mesh x, y, p. What do we get? Something not very good. Oh, there we go. So that's what my mesh plot looks like. Pretty cool. Okay, so you can see that this is exactly kind of the behavior we expect. We've got a producer over, we've got an injector, so we got high pressure over here and low pressure at the producer right in the center, right? So that's the kind of thing we expect. You could do a surface. Okay. I'm going to show you another trick. So, okay, something really cool. So I think these surface plots look better if I go in and I edit the figure. And I click on it, and then I go in here and I say no line on the edges. Close that. And it kind of comes out like that. And I think it looks better like that. So that's just a little trick. What else? Well, I actually asked you to use a contour plot. You use the contour XYP. This is a contour plot right here. You could use more contours. If I did 100, see what happens there. No, it doesn't like that. Maybe 20. No, it doesn't like that either. There's a way to do more contours. I forget what it is. Let's do contour F, though. Contour F. Okay. I don't like, so what I'm going to do is I'm going to go to help because I forget how to do the more. So I'm going to go plug in contour. In contour level. So I think I was doing it right. Maybe I just had too many, too few. So let me do contour FP. Let me do 10 contours. Well, it doesn't like that, does it? Well, I'm doing something wrong. Well, anyway, if you read in here, you can learn more about how to have more contour lines and make a little bit better plot. So that's something that you should maybe look in and see what you can find. But that's basically what we're looking at, right? So I had contour. You get some contouring lines over there, and you can see the pressures are over that. And you can do a lot of different things if you read in the help. It tells you how you can put in different types of different comments, and you can number things and different colors and stuff like that. Maybe I want to put a legend. So just as always, I can do a legend, pressure, plot. So you can see I got my legend there. Something else. Let me do the surf plot again. You do surf plot like that. This is what we got over there. Look like that. You can do a color bar. We do the color bar. It shows you the different values, what the colors mean, and how they correspond to that. So it's always a good idea to put your color bar there as well. But that's some more stuff about 3D plotting. So we kind of finished 2D and 3D plotting today. And again, as always, I just kind of scratch the surface, and I don't know everything, but I just try to share some things that I know. When in doubt, go to Google, go to Matlab Help, and you can learn a whole lot more tools. But hopefully what you learn in today's session on plotting is enough to kind of get you by and teach you the bare minimum. But with that, that finishes the third part of our Matlab review session.